For fluorescent lighting, the answer is yes. You should still derate the feeders for the panel if the neutral is carrying current. This is because the National Fire Protection Association 70, otherwise known as the National Electrical Code, requires that the neutral be treated as a current-carrying conductor for fluorescent lighting installations. The reason for this is that the high harmonic content in the current waveform of fluorescent ballast can cause neutral currents to be up to 200% of the phase current. Now, considering a panel with all computer loads, if the panel has a double-sized neutral, you may not need to derate the wire if certain conditions are met. Firstly, the neutral is properly bonded to the equipment grounding conductor at the service entrance. Secondly, the equipment grounding system is properly installed and maintained. Thirdly, the loads do not generate significant harmonics. However, it is always a good practice to verify with the local electrical inspector to confirm the requirements for the specific installation. In general, derating the wire is not necessary if the neutral is properly bonded and the system is properly grounded. However, it is important to consult with the local electrical inspector to confirm the requirements for the specific installation. To elaborate further on neutral conductors, especially in the context of fluorescent lighting and computer loads, it's crucial to understand the role of harmonics. Harmonics are sinusoidal waveforms that are multiples of the fundamental frequency, which is typically 60 Hz in the United States. Nonlinear loads, such as fluorescent ballasts and computer power supplies, draw current in short, abrupt pulses rather than in a smooth sinusoidal manner. This generates harmonic currents that flow back to the source. These harmonic currents can cause several problems. One problem is increased neutral current. In a balanced three-phase system with purely linear loads, the neutral current is theoretically zero. However, when harmonic currents are present, particularly third harmonic currents and its multiples, these currents add up arithmetically in the neutral conductor instead of cancelling out. This can result in a neutral current that exceeds the phase currents, potentially overloading the neutral conductor. Another problem is voltage distortion. Harmonic currents flowing through the impedance of the electrical system cause voltage distortion. This distorted voltage can affect the performance of other equipment connected to the same system, leading to malfunctions or reduced lifespan. Additionally, there is increased heating in equipment. Harmonic currents increase the root mean square current flowing through conductors, transformers, and other equipment. This leads to increased heat generation, which can degrade insulation and reduce the lifespan of the equipment. The National Electrical Code addresses the issue of harmonic currents and neutral conductors in several ways. It requires that the neutral conductor be sized to carry the maximum unbalanced load, which may include harmonic currents. It also requires that the neutral conductor be treated as a current-carrying conductor in certain situations, such as when the majority of the load consists of nonlinear loads. Furthermore, the NEC provides guidance on derating conductors to account for the effects of harmonic currents. Derating factors are applied to the ampacity of conductors to reduce their allowable current carrying capacity. This is done to prevent overheating and ensure that the conductors operate within their safe temperature limits. Now, let's dive deeper into the specific cases of fluorescent lighting and computer loads. Fluorescent lighting typically uses electronic ballasts, which are a type of nonlinear load that generates significant harmonic currents, particularly third harmonic currents. As a result, the neutral conductor in a fluorescent lighting circuit can carry a substantial amount of harmonic current, potentially exceeding the phase current. For this reason, the NEC requires that the neutral conductor be treated as a current-carrying conductor in fluorescent lighting circuits. This means that the neutral conductor must be included when determining the number of current-carrying conductors in a conduit or cable, which affects the ampacity derating factors that must be applied. In the case of computer loads, the situation is more complex. Computer power supplies are also nonlinear loads that generate harmonic currents. However, the amount of harmonic current generated by a computer load depends on several factors, including the type of power supply, the load and the power supply, and the power factor correction circuitry used in the power supply. Some computer power supplies have power factor correction circuitry that reduces the amount of harmonic current generated. In these cases, the neutral current may not be significantly higher than the phase current. However, other computer power supplies do not have power factor correction circuitry and can generate significant harmonic currents. In these cases, the neutral current can be significantly higher than the phase current, especially when multiple computers are connected to the same circuit. If a panel exclusively serves computer loads, and the neutral is double-sized, derating may not be required provided the conditions previously stated are met. These conditions ensure proper bonding and grounding, and minimal harmonic generation. However, local electrical inspectors hold the final authority on compliance and specific installation requirements. It's always prudent to confirm these requirements to ensure a safe and compliant electrical system. Let's also consider the role of grounding in mitigating harmonic issues. A properly installed and maintained equipment grounding system is essential for providing a low impedance path for fault currents to flow back to the source. This helps to protect equipment and personnel from electrical shock. It also helps to reduce the amount of voltage distortion caused by harmonic currents. The equipment grounding conductor should be sized according to the requirements of the NEC and should be properly bonded to all metal enclosures, raceways, and equipment. In addition to the equipment grounding conductor, a supplemental grounding electrode system may be required in some cases. A supplemental grounding electrode system consists of one or more grounding electrodes, such as ground rods or ground plates, that are connected to the equipment grounding system. This helps to further reduce the impedance of the grounding system and improve its effectiveness. Now, let's address some common misconceptions about neutral conductors and harmonic currents. One common misconception is that the neutral conductor only carries the unbalanced load. While it is true that the neutral conductor carries the unbalanced load in a balanced three-phase system with purely linear loads, it also carries harmonic currents, which can significantly increase the total current flowing through the neutral conductor. Another common misconception is that a double-sized neutral conductor is always sufficient to handle harmonic currents. While a double-sized neutral conductor can help to reduce the voltage drop and temperature rise in the neutral conductor, it may not be sufficient to handle all of the harmonic currents generated by nonlinear loads. It is important to carefully evaluate the harmonic content of the load and size the neutral conductor accordingly. A further misconception is that power factor correction always eliminates harmonic currents. While power factor correction can reduce the amount of harmonic current generated by a load, it does not always eliminate it completely. Some power factor correction circuits only correct for the fundamental frequency and do not address harmonic currents. In these cases, additional measures may be needed to reduce the amount of harmonic current flowing through the neutral conductor. To ensure a safe and reliable electrical system, it is essential to follow the requirements of the NEC and consult with a qualified electrical engineer or contractor. The NEC provides detailed guidance on sizing conductors, derating conductors, grounding systems, and other aspects of electrical system design and installation. A qualified electrical engineer or contractor can help you to design and install an electrical system that meets your specific needs and complies with all applicable codes and standards. When dealing with harmonic currents, it is often helpful to perform a harmonic analysis. A harmonic analysis is a study that measures the harmonic content of a current and voltage waveforms in an electrical system. This information can be used to identify potential problems and develop solutions to mitigate the effects of harmonic currents. A harmonic analysis can be performed using a variety of instruments, such as a power quality analyzer or a spectrum analyzer. The results of the harmonic analysis can be used to size conductors, select appropriate grounding systems, and install harmonic filters. Harmonic filters are devices that are designed to reduce the amount of harmonic current flowing through an electrical system. They work by providing a low impedance path for harmonic currents, which diverts the harmonic currents away from the neutral conductor and other sensitive equipment. There are two main types of harmonic filters: passive filters and active filters. Passive filters consist of inductors, capacitors, and resistors that are tuned to specific harmonic frequencies. They are relatively inexpensive and easy to install, but they can only filter a limited number of harmonic frequencies. Active filters use electronic components to dynamically cancel out harmonic currents. They are more expensive and complex than passive filters, but they can filter a wider range of harmonic frequencies and can adapt to changing load conditions. In addition to harmonic filters, other measures can be taken to reduce the effects of harmonic currents. These measures include using power factor correction equipment, using harmonic mitigating transformers, and separating nonlinear loads from sensitive equipment. Power factor correction equipment can reduce the amount of harmonic current generated by a load. Harmonic mitigating transformers are designed to reduce the amount of harmonic current that is transferred from the primary side of the transformer to the secondary side. Separating nonlinear loads from sensitive equipment can help to prevent voltage distortion and other problems caused by harmonic currents. Let's consider some examples of how these principles apply in real-world scenarios. Suppose you are designing an electrical system for an office building that will have a large number of computers and fluorescent lights. In this case, you would need to carefully consider the harmonic content of the load and size the neutral conductor accordingly. You might also need to install harmonic filters to reduce the amount of harmonic current flowing through the neutral conductor and other equipment. Alternatively, suppose you are troubleshooting a problem in an existing electrical system that is experiencing voltage distortion and the equipment malfunctions. In this case, you would need to perform a harmonic analysis to identify the source of the harmonic currents. You might then need to install harmonic filters or take other measures to reduce the effects of the harmonic currents. In conclusion, understanding neutral conductors, harmonic currents, and the requirements of the National Electrical Code is essential for designing and maintaining safe and reliable electrical systems. By carefully considering the harmonic content of the load, sizing conductors appropriately, installing proper grounding systems, and taking other measures to mitigate the effects of harmonic currents, you can ensure that your electrical system operates efficiently and safely. Remember to always consult with a qualified electrical engineer or contractor for assistance with electrical system design and installation. They can help you to design and install an electrical system that meets your specific needs and complies with all applicable codes and standards. They can also help you to troubleshoot problems in existing electrical systems and develop solutions to mitigate the effects of harmonic currents. By working with a qualified professional, you can ensure that your electrical system is safe, reliable, and efficient. Furthermore, ongoing maintenance and periodic inspections are crucial for maintaining the integrity of electrical systems, particularly those susceptible to harmonic-related issues. Regular thermal imaging can detect hotspots caused by excessive harmonic currents in conductors and equipment, allowing for proactive intervention before failures occur. Similarly, monitoring power quality parameters such as total harmonic distortion can provide early warnings of potential problems. In addition to technical considerations, it's also essential to educate users about the impact of their equipment on the electrical system. Encourage the use of energy-efficient appliances and devices with power factor correction to minimize harmonic generation. Implementing policies that promote responsible energy consumption can also contribute to a healthier electrical environment. When upgrades or modifications are made to an electrical system, it's crucial to reassess the harmonic profile of the load and make necessary adjustments to conductor sizing, grounding, and filtering. Failure to do so can lead to unforeseen problems and compromise the system's reliability. Finally, staying informed about the latest advancements in electrical technology and best practices is essential for maintaining a state-of-the-art electrical system. Participate in industry training programs, attend conferences, and subscribe to relevant publications to stay abreast of emerging trends and innovative solutions. By embracing continuous learning, you can ensure that your electrical system remains safe, efficient, and resilient in the face of evolving technological challenges. Also be sure to look at National Electrical Code Table 3.1015b3, which covers adjustment factors for more than 3 current carrying conductors in a raceway or cable. Always follow the NEC